There is a region of space so empty that if our galaxy sat at its center, we would have thought we were alone in the universe. 300 million light-years across, a volume that should hold 2,000 galaxies. Scientists found 60. 60. We are going to go inside it, figure out how it got there, why it keeps growing, and why it may be breaking our best model of how the universe works. If you enjoy the journey, subscribe. You won't want to miss where this goes. Prepare yourselves. We begin. The year was 1981. A team of astronomers sat down to map a slice of the universe, galaxy by galaxy, and one of them noticed something wrong. Robert Kirshner had spent years studying how galaxies spread across space. His team was running what scientists call a redshift survey. The idea was simple. Point a telescope at a patch of sky. Measure how fast each galaxy is moving away from us. Use that speed to calculate its distance. Then plot every galaxy on a map and see what the universe actually looks like in 3 dimensions. They expected a bumpy map. Dense clusters here, thin walls there. The universe is lumpy, and everyone knew it. What they found instead stopped the room cold. One region had almost nothing in it. A volume of space so wide it should have held roughly 2,000 galaxies showed up almost completely blank. Kirshner's team plotted it again. Same result. They checked their instruments. Still blank. This was not a gap caused by a star blocking the view or a technical error in the equipment. Galaxy after galaxy was simply absent across a stretch of space that made the minds of everyone in that room struggle to hold the scale of it. The region sits in the direction of the constellation Boötes, the herdsman, a pattern of stars visible on summer nights in the northern hemisphere. Astronomers named the empty region the Boötes Void. Colleagues who heard about it early called it something simpler, the Great Nothing. Now here is where your sense of scale is going to get tested. Light travels about 6 trillion miles in a single year. 1 light year equals 6 trillion miles. The Boötes Void stretches somewhere between 250 and 330 million light-years across. Write out what that distance looks like in miles, and you get a number with so many zeros it stops meaning anything to the human brain. A better way to picture it: if you shrank the entire Milky Way galaxy down to the size of a quarter, the Boötes Void would still be about the size of a football field. Our entire galaxy, a coin; the void, a field. That blank region sat inside the universe all along. Billions of years passed. Stars were born and died. Civilizations came and went on whatever worlds might exist out there. And through all of it, this enormous pocket of space stayed nearly empty while the rest of the universe filled with light and structure around it. Kirshner published the findings, and the astronomical community paid attention fast. A region that large and that empty forced a serious question. Was this a freak accident of cosmic history? Or was there something about the way the universe builds itself that naturally produces empty places on this scale? And if it does, why had no one predicted one this big? The mystery deepened quickly, because when follow-up surveys pointed telescopes back into the void to count the galaxies more carefully, they found something even stranger than the emptiness itself. The 60 galaxies that do exist inside this enormous region are arranged in a shape that makes no sense if the void formed the way astronomers expected. They do not scatter randomly through the volume. They line up, a thin tube of galaxies running through the middle of the void like a spine through an empty chest. That shape is a clue, and it points toward an origin story far weirder than a simple empty patch of space. Before 1981, most people imagined the universe as a kind of fog. Galaxies everywhere, spread out more or less evenly, with some clumping here and there. That picture felt reasonable. The universe is enormous. Surely things average out. Redshift surveys destroyed that idea. Here is how they work. When a galaxy moves away from us, the light it sends out gets stretched. The wavelength grows longer. On the visible light spectrum, longer wavelengths push toward the red end. Scientists call this redshift. The faster a galaxy moves away, the more its light shifts toward red. Measure the shift, and you know the speed. Use the speed and the universe's known expansion rate, and you can calculate roughly how far away the galaxy sits. Plot enough of those distances on a map, and the three-dimensional structure of the universe starts to appear, like watching a city materialize out of fog as you drive toward it. Before this technique became standard, astronomers could only see the sky in two dimensions, like a flat photograph. Everything appeared at the same depth. A galaxy a million light-years away and one a billion light-years away both showed up as tiny smudges in the same flat image. Redshift surveys added the missing dimension, depth, and when depth appeared, the universe looked nothing like a fog. It looked like a web, dense filaments of galaxies stretched across enormous distances. Flat walls of galaxies, some hundreds of millions of light-years wide, sat between the filaments, and between those walls and filaments sat enormous empty regions. Voids. The universe was not a smooth fog at all. It was more like the inside of a giant sponge, with matter packed into the walls and almost nothing in the spaces between them. Kirshner's team was mapping one of those spaces when they found Boötes. The survey that revealed it covered only a small fraction of the sky, which means the team was not even trying to find something record-breaking. They were doing routine work, cataloging galaxies in a strip of sky to understand the local structure of the universe. The blank region appeared in their data by accident. That accidental discovery matters for a reason that goes beyond one strange void. It proved that the universe builds structure on scales far larger than anyone had seriously modeled. Before Boötes, most cosmological models predicted clumping and structure up to a certain size, then smoothness beyond that. Boötes showed that the universe produces dramatic emptiness at scales the models had not fully accounted for. Scientists had to go back and ask how the universe could possibly build something that big and that empty through ordinary physics alone. The answer they found starts long before any galaxy ever formed. It starts in the first fractions of a second after the Big Bang, when the universe was smaller than a marble and already beginning to develop tiny differences in density that would eventually grow into everything we see today. Those differences were almost invisible at first. Barely a whisper of extra matter here, barely a whisper less there. But gravity is patient. It works across billions of years. And what began as the faintest ripple in the early universe eventually carved the cosmic web, galaxy by galaxy, filament by filament, and void by void. Understanding what came next requires understanding the web itself, because the Boötes void did not form in isolation. It formed inside a universe that was actively building the largest structure in existence. And the scale of that structure is going to reset everything you thought you knew about how big things can get. Picture the biggest spiderweb you have ever seen. Now make each strand 100 million light-years long. Make each junction where strands meet a city of galaxies so dense that thousands of them crowd together. Make the empty spaces between the strands vast and cold and almost silent. That is the cosmic web. It covers the entire observable universe. Every galaxy we have ever seen sits somewhere inside it, either packed into a dense node, stretched along a filament, or sitting on a flat wall. The Boötes void is one of the enormous empty pockets between those walls and filaments. The cosmic web did not always exist. In the very early universe, matter was spread out in an almost perfectly even soup. Temperature, density, and pressure were nearly identical everywhere, but nearly is the key word. Tiny differences existed. Regions where matter was just barely more concentrated began to pull in neighboring matter through gravity. Regions where matter was just barely less concentrated began losing material to their denser neighbors. Think of it like money. If two people start with almost the same amount and one of them earns just slightly more interest, after a few years the gap is bigger. After a few decades, it is dramatic. After a few centuries, it is enormous. The universe runs on the same compounding logic, except the currency is matter and the time frame is billions of years. Over time, the dense regions grew denser. Gravity pulled more and more matter toward them. The less dense regions kept losing material. What started as nearly invisible ripples in the early universe sharpened into the filaments and voids we see today. Scientists mapped the full structure of the cosmic web using surveys that cover enormous portions of the sky. When they plot the positions of millions of galaxies, the web appears clearly: long, glowing strands, dense, bright clusters where strands meet, and between them, dark, empty regions that stretch for hundreds of millions of light years in every direction. The Boötes void sits inside one of those dark regions. Now here is the part that pushes the scale even further. The filaments themselves are not the largest structures in the web. There are walls, flat sheets of galaxies so enormous they dwarf even the largest filaments. One of them, called the Hercules Corona Borealis Great Wall, spans roughly 10 billion light years. If you placed it next to the Boötes void, the void would look like a small pocket in one corner of something almost incomprehensibly bigger. The cosmic web is the largest known structure in the universe. Everything else, every galaxy, every star, every planet, exists inside it or between its strands. And the void fits into that web the way an air bubble fits inside a brick. The surrounding structure is dense, active, full of light and gravity. The void is the space that matter left behind. Understanding how matter leaves a region takes us into one of the stranger and less discussed parts of cosmology. Because matter does not just stop being in a place, it gets pulled out, slowly, steadily, across billions of years. Something pulls galaxies toward the web's dense filaments and away from the empty region. That pulling force is gravity. But the way it works inside a void, across those distances and over those timescales, is where things get genuinely strange. The word void sounds like a hole, a rip, a place where space itself tears open and nothing remains. The reality is stranger and in some ways harder to picture. A cosmic void is a region where matter is far less concentrated than the universe's average. Space still exists inside a void. Light still passes through it. The laws of physics still apply in every corner of it. What is missing is the stuff that usually fills space: galaxies, galaxy clusters, gas clouds, and the dark matter that ties all of those things together. A void is not empty. It is drastically underdense. Picture a city. Downtown has skyscrapers packed together, millions of people, constant activity. Then you drive about 2 hours out and find farmland. A few houses separated by miles of open field. The farmland is not nothing. It has soil, air, the occasional tree, but compared to downtown, it feels abandoned. A cosmic void is like that farmland, except the nearest city is hundreds of millions of light years away, and the farmland stretches for a distance no car could ever cross. The universe produces voids constantly because gravity creates winners and losers. Dense regions win. They pull in more matter, grow denser, attract even more. Low-density regions lose. They give up their matter to the surrounding denser zones and grow emptier. The result is a universe where matter piles up in some places and abandons others. Most voids are relatively small, tens of millions of light years across, numerous and distributed throughout the cosmic web, filling the spaces between the filaments the way air fills the holes in a sponge. Scientists have catalogued thousands of them. Then there are supervoids. These are the rare, extreme cases where the emptiness reaches a scale that challenges the models. The Boötes void is one of the most famous supervoids ever found. Somewhere between 250 and 330 million light-years across, it ranks among the largest known voids in the observable universe. What makes supervoids unusual is not just their size, it is what their size implies. Forming something that large and that empty requires a very specific set of conditions across billions of years of cosmic history. The matter that drained out of the Boötes region did not just drift away overnight. The process unfolded across timescales that started near the beginning of the universe itself. Voids also have boundaries. The edge of a void is where the underdense region transitions back into the filaments and walls of the cosmic web. At that boundary, you find more galaxies, more gas, more structure. If you could fly from the center of the Boötes void toward its edge, the sky would gradually fill in around you. At first, just the 60 lonely galaxies of the void's interior. Then, approaching the boundary, clusters and filaments would start to appear, growing denser as you crossed into the surrounding web. Standing at the edge, looking inward and outward at the same time, you would see two completely different universes separated by a few million light-years of gradual transition. The fact that voids have boundaries raises a question that cosmologists take seriously. If matter flows out of voids and into filaments, does the void shrink over time as it loses its edges? Or does it grow, swallowing more territory as the emptiness deepens? The answer is more surprising than most people expect, and it shapes everything about how we understand what is happening inside Boötes right now. Size is the first thing that separates the Boötes void from every other void in the universe that astronomers had found before it. 250 to 330 million light-years across. Those numbers appear in astronomy articles regularly, and they get noted and moved past. But they deserve to sit for a moment, because the implications of that size are what made Boötes famous and what still make it scientifically uncomfortable today. The observable universe stretches about 93 billion light-years from one side to the other. The Boötes void spans roughly 300 million of those light-years. That sounds like a small fraction until you start thinking about what structures exist across the rest of that space. The Milky Way galaxy is about 100,000 light-years across. 100,000. The Boötes void is roughly 3,000 times wider than our entire galaxy. If you placed the Milky Way at one edge of the void and tried to reach the other side traveling at the speed of light, you would spend 300 million years in transit. The universe itself is only about 13.8 billion years old. That crossing would consume more than 2% of all of cosmic time. When astronomers first estimated the void's size from Kirshner's survey data, many colleagues assumed there had to be a mistake. The standard models of cosmic structure formation, the ones that describe how matter clusters and how voids form, predicted that voids should reach a certain maximum size based on the physics of the early universe. A void the size of Boötes pushed right up against and possibly past the upper limit those models allowed. The concern was not just about one strange region. The concern was about whether the models themselves were telling the full story. If the universe can produce a void 300 million light-years across through ordinary physics, then either the physics is right and this void got extremely lucky, or the physics is missing something. Both options are unsettling in different ways. A lucky accident of that magnitude is exactly what statistical models say should almost never happen, and a gap in the physics means the most successful cosmological model in history, the framework that accurately describes everything from the Big Bang to the cosmic web, has a hole in it. The size also raised a timing problem. Building a void that large requires matter to drain out of the region over an enormous amount of time. The universe is old, but is it old enough? Did the physics of the early universe create the right starting conditions for a void this extreme to develop naturally? Some early calculations suggested the answer was barely yes. Others suggested it was uncomfortably close to no. Astronomers pushed forward with more surveys, more data, more calculations. And when they looked more carefully at the numbers, they found something that shifted the conversation completely. The void was not just large, it was nearly empty in a way that made simple drainage explanations feel thin. 2,000 expected galaxies, 60 found. That ratio, that 97% deficit, pointed toward a process more extreme than normal void formation. Something had either drained this region with unusual efficiency, or the void had a more complex origin than a single empty bubble forming and growing on its own. What that origin might be is where the story gets genuinely strange. Walk into a forest and start counting trees. Based on the density of the forest around you, you can make a reasonable guess about how many trees should stand in any given acre of land. If you walk into an acre and find 3 trees where you expected 200, you stop and look around. Something happened here. That is exactly what astronomers did with the Boötes void. The calculation is not complicated in principle. Scientists know roughly how many galaxies exist per unit of volume across the observable universe. Take the average galaxy density, multiply it by the volume of the Boötes void, and you get an expected count. A region that size, filled with matter at the universe's average density, should contain somewhere around 2,000 galaxies. Kirshner's team found 60 galaxies in a space built for 2,000. The deficit is so large it is hard to frame properly. Imagine a parking lot designed for 2,000 cars. You drive in and find 60. You do not assume the other drivers are just running late. Something is structurally different about this parking lot. The mathematical expectation was not a rough guess. It was grounded in the same models that accurately predict galaxy counts across hundreds of other regions of the sky. Those models work. They match observations in dense clusters, in average filaments, in small, ordinary voids. They have been tested and refined for decades. The Boötes void is one of the places where the gap between prediction and observation is widest. A 97% deficit in galaxy count is extraordinary. Scientists working in fields outside astronomy sometimes borrow the term Six Sigma event to describe something so far outside the expected range that it falls beyond almost all statistical probability. The galaxy count inside the Boötes void approaches that kind of rarity. Now, here is the part that complicates the math further. The 60 galaxies astronomers have found inside the void may not represent a complete count. The surveys that mapped the void were sensitive to bright, large galaxies. Fainter, smaller galaxies are harder to detect at those distances. There could be additional dwarf galaxies scattered through the void that current instruments have not picked up. Some estimates suggest the true count might be higher, possibly several hundred if you include every type of galaxy at every brightness level. But even if the real number is several hundred, the expected number is still 2,000. The deficit remains dramatic, and the galaxies that have been identified still show that strange tube-like arrangement clustered along a rough line through the void's interior rather than scattered evenly throughout the volume. That distribution matters. If galaxies simply failed to form inside the void, you would expect the few that did form to sit randomly wherever local conditions allowed. The fact that they line up suggests the void's interior has structure. Something shaped the arrangement of those 60 galaxies. Some pattern in the void's history left a mark on where matter settled. That pattern is a clue about how the void formed, and following that clue leads directly into one of the most fascinating and underreported ideas in cosmology: the possibility that the Boötes void is not one thing, but many things merged into one. That the emptiness we see today is the combined product of a long history of smaller, older, empty regions that stitched themselves together over billions of years. Imagine standing on a planet inside the Boötes void and looking up at the night sky. On Earth, a clear night reveals thousands of stars. On a dark enough night, far from city lights, you can see the faint smear of the Milky Way itself. Hundreds of billions of stars blending into a soft band of light. The sky feels full, crowded, even. Inside the Boötes void, that sky would be almost completely dark. The nearest large galaxy outside the void would sit hundreds of millions of light years away. At that distance, it would not be visible to the naked eye. Even with a powerful telescope pointed outward, the galaxy clusters surrounding the void would appear as faint smudges at the extreme edge of detection. The void's interior is so far from the dense filaments of the cosmic web that looking outward from inside it would feel like looking through a dark window with nothing on the other side. But there are 60 galaxies in there. 60 is a precise count, based on what current surveys have identified with confidence. These are real galaxies, each containing billions of stars, each with their own histories of formation, star death, and chemical evolution. They exist inside the void. They are just extraordinarily spread out. If you distributed 60 objects evenly through a volume 300 million light-years across, the average distance between neighbors would be enormous. In the cosmic web, Galaxies crowd together in clusters, where dozens or hundreds sit within a few million light-years of each other. Inside the Boötes void, the nearest galaxy to any given one could easily be tens of millions of light-years away. Each of those 60 galaxies drifts in a kind of isolation that the Milky Way has never experienced. Now, here is what makes those 60 galaxies more than just a count. They are not spread evenly through the void. Scientists who mapped their positions found that many of them cluster along a rough line through the void's interior, a tube-like arrangement running through the middle of the empty region. Some researchers describe it as a cylinder, others call it a spine. Either way, the shape is distinct enough that it shows up repeatedly in follow-up studies. A random distribution of galaxies left over from a simple, smooth void forming and emptying would not produce a tube. Random scatter would fill the volume, however, sparsely. The fact that the galaxies line up suggests that the void's interior has memory. Whatever process created the void left a physical signature in the positions of the galaxies that survived inside it. That signature is what makes the tube-shaped galaxy distribution one of the most scientifically interesting details of the Boötes void. It is a fossil, a trace of the void's origin story, preserved in the arrangement of the few galaxies that never got pulled out. And that origin story, the one written in the positions of 60 lonely galaxies across 300 million light-years, points toward a history far more complex than a single empty region forming and growing in place. It points toward collision, mergers, the joining of multiple older, smaller voids into one enormous composite structure. The tube of galaxies may be the boundary where two of those older voids once met, the seam where separate emptinesses fused into one. If that is right, then the Boötes void is a scar, and reading that scar correctly could tell us something fundamental about how the universe builds its largest empty spaces. The tube is the detail that most popular descriptions of the Boötes void skip over. That is a mistake, because the tube is where the physics gets genuinely interesting. When astronomers catalogued the positions of the galaxies inside the void, the arrangement that emerged was not random. Many of the galaxies trace a rough cylindrical path through the void's interior. Picture a long, hollow tunnel made of scattered light, running through an otherwise dark space. That is what the distribution looks like when plotted in 3 dimensions. A random scatter of surviving galaxies would produce a roughly even distribution throughout the volume, maybe with some local clumping due to small-scale gravity between neighboring galaxies. The tube shape requires a different explanation. The leading idea connects to how voids merge. When two separate void regions grow large enough that their boundaries approach each other, the walls between them can thin and eventually break down. Matter that once sat at the shared boundary gets redistributed. Some of it gets absorbed into the surrounding filaments. Some of it remains, stranded at what was once the edge of 2 distinct voids, but is now the interior of one combined empty region. That stranded matter becomes the galaxies we find inside. They mark the old seam. Think of 2 soap bubbles touching. Where the surfaces meet, they share a thin film of material. If the 2 bubbles merge into one larger bubble, that shared film collapses. Some of the material that made up that film stays inside the new, larger bubble. If you could photograph the inside of the combined bubble, you would see a faint trace of where the old walls used to sit. The 60 galaxies of the Boötes void may be exactly that, the faint trace of an old wall between 2 or more smaller voids that merged billions of years ago. This merger hypothesis also explains a second observation. The galaxies inside the Boötes void are not all the same age. Some appear older than others. If the void had formed as a single, simple, empty region from the beginning, you might expect the survivor galaxies to share a roughly similar formation history. The age variation hints that the galaxies came from different parts of a more complex structure, regions with different environmental histories that got swept together when the voids joined. The tube shape also hints at the direction of the old boundary. The cylinder runs along what would have been the contact surface between two merging void regions. The orientation of the tube, when compared to the surrounding cosmic web, lines up in a way that makes sense given where the nearest filaments and walls sit. Matter moved along those filaments and shaped the boundary of the older voids before they merged. The tube remembers the direction of that movement. None of this is settled science. The merger hypothesis is the leading explanation, and it fits the available data better than alternatives. But the surveys that produced the current galaxy positions were not designed with high-precision mapping of the void's interior in mind. Future telescope missions, with better sensitivity and wider sky coverage, will produce a far clearer picture of exactly where those galaxies sit and how their arrangement matches the predictions of the merger model. Until then, the tube sits there in the data, a shape that should not exist if the void is simple, a shape that makes perfect sense if the void is ancient and complex. Something even stranger is waiting in the physics of how that merger happened, because voids do not merge the way galaxies do. Gravity has a reputation for pulling things together. Stars form because gravity squeezes gas clouds until they ignite. Galaxies form because gravity draws stars into rotating disks. Clusters of galaxies form because gravity hauls entire galaxies toward each other across millions of light years. But gravity also empties things out. The mechanism is one of the less obvious consequences of the same force. When a region of space has slightly less matter than its surroundings, the surrounding denser regions exert a stronger gravitational pull. The matter at the edge of the low-density region gets tugged outward toward those denser zones. Over time, the low-density region loses material from its edges. It grows emptier. It also grows slightly larger, because as matter leaves, the boundary of the underdense region expands inward, meaning the region where density falls below average covers a greater volume. This process is slow, glacially slow by human standards, but on cosmic timescales, across billions of years, it carves the universe into the pattern of the cosmic web. The Boötes void has been emptying since the early universe. The seeds of its underdensity formed in the first moments after the Big Bang, when the distribution of energy was almost but not perfectly uniform. The region that would eventually become the Boötes void started with slightly less matter than its neighbors. Gravity did the rest. Picture a bathtub with a small drain. The water near the drain moves toward it first, then water from farther away follows. Over hours, the tub empties. The cosmic void works on the same principle, with one difference. The drain is not at the center. The drain is everywhere along the boundary. Matter flows outward in all directions, toward the dense filaments that surround the void, pulled by the combined gravitational attraction of everything in the cosmic web beyond. What stays behind? Whatever matter was too isolated from the boundary to get swept up, galaxies deep in the void's interior, far enough from any filament that the gradient of gravitational pull never grew strong enough to carry them out. Those are the 60 galaxies. The ones gravity could not reach efficiently before the void had already grown too wide for the pull to be effective. There is also another layer to the drainage story. As the void empties, its interior becomes even less dense. A less dense interior exerts less gravity on its remaining contents, making it even harder for those contents to gather and form new structure. Galaxy formation inside the void slows down and eventually nearly stops. The 60 galaxies inside Boötes are mostly older galaxies. New star formation inside those galaxies is suppressed compared to galaxies living in the dense, gas-rich environment of a filament. In the void, galaxies age without feeding. They burn through their existing gas, form fewer new stars, and slowly redden as their youngest, hottest stars burn out and are not replaced. A galaxy inside the Boötes void looks different from a galaxy of the same age living in a dense cluster. The environment shapes the galaxy itself. This means the void is not just a region of missing galaxies. It is a region of altered galaxies. And what happens to matter once it is gone from a void raises questions about whether that matter ever comes back. Everything in the universe, every galaxy, every filament, every void, traces back to the first fraction of a second after the Big Bang. The universe began unimaginably hot and dense. As it expanded, it cooled. Matter and energy were locked together in a near-perfect soup. But near-perfect is the critical phrase. The soup had wrinkles, tiny fluctuations in density, smaller than anything you could measure in a lab, spread through the early universe like ripples on the surface of a pond. Those ripples were quantum in origin. At the smallest scales of physics, uncertainty is built in. The early universe was small enough that quantum fluctuations left imprints on the distribution of matter across the entire cosmos. Those imprints, laid down in the first moments of existence, became the seed of every structure we see today. Think of it this way. You flatten a piece of wet paper and let it dry. The sheet is mostly flat, but it has tiny imperfections, microscopic bumps, and wrinkles from the water and the surface it dried on. Once dry, those wrinkles stay. Now imagine the sheet expanding. As it grows, the bumps grow with it. Wrinkles that were too small to see become folds you can feel. Folds become ridges. Ridges become mountains. The initial imperfection, barely there at the start, becomes the dominant feature over time. That is the universe. The cosmic web, with all its filaments and voids, is a vastly magnified image of quantum noise from the first instant of time. Scientists have actually mapped the pattern of those early fluctuations. The cosmic microwave background is the light left over from when the universe first cooled enough for atoms to form, about 380,000 years after the Big Bang. It fills the entire sky, and it is not perfectly smooth. It has tiny temperature differences, hot spots and cold spots, a fraction of a percent different from the average. Those temperature differences map directly onto the density differences from the early universe. Hot spots correspond to slightly denser regions. Cold spots correspond to slightly less dense regions. And when you compare the map of the cosmic microwave background to the map of the modern cosmic web, the patterns match. The same regions that were slightly underdense in the baby universe are the locations of voids in the universe today. The Boötes void began as a cold spot, a region of the early universe where the quantum fluctuations left slightly less matter than average. Over nearly 14 billion years, gravity amplified that slight deficit into a supervoid 300 million light-years across. The process was inevitable once the initial conditions were set. No external force created the Boötes void. No explosion cleared it out. The emptiness grew from within, driven by the mathematics of gravity acting on the faintest whisper of asymmetry in the first moments of existence. And yet, knowing the mechanism does not make the scale of the result feel any less strange. The universe amplified a quantum hiccup from its infancy into one of the largest empty regions ever found. If those early ripples had been arranged slightly differently, the void might not exist, or a different region might have become the great nothing instead. The void's origin is written in the oldest light in the universe, and that light contains even more secrets than the void itself. Two bubbles in a bathtub touch. The thin wall between them holds for a moment. Then it pops. One larger bubble takes the place of two smaller ones. Cosmic voids work the same way, across scales and timescales that make the soap bubble analogy feel laughably small. The universe produces voids of all sizes. Small voids, tens of millions of light-years across, fill the spaces between galaxy filaments throughout the cosmic web. These voids form early, when the matter that will become filaments first starts draining away from low-density regions. As the universe ages and matter continues moving toward denser zones, the boundaries of neighboring voids draw closer together. When two void boundaries meet, the wall of galaxies and matter separating them begins to thin. The wall is held together by gravity, but the gravity pulling matter from both sides of it toward the surrounding filaments eventually wins. The wall drains. What remains after the draining is one larger empty region where two smaller ones used to be. This process has a name, void merging, and it is considered one of the leading explanations for how the Boötes void reached its current enormous size. The idea is straightforward. Start with several smaller voids, each maybe 50 to 100 million light-years across, sitting near each other in the same region of the universe. Over billions of years, each void empties and expands slightly. Their boundaries approach, the walls between them thin. One by one, the walls collapse and the voids join. What you end up with is a single giant void that looks smooth and simple from the outside, but carries the marks of its history inside. Those marks are the galaxies that used to sit in the walls between the smaller voids. They did not get absorbed into the surrounding filaments quickly enough. They ended up stranded inside the merged void, tracing the lines of the old boundaries. This is the explanation that many astronomers find most convincing for the tube of galaxies inside the Boötes void. Those 60 galaxies are the remnants of old walls. The tube shape follows the boundary of one of the smaller voids that merged into the present-day structure. The tube is geological, in a cosmic sense. It is a layer in the rock that tells you where an old surface used to be. The merger hypothesis makes a specific prediction that future surveys can test. If the void formed through mergers, the detailed positions and ages of the galaxies inside should reflect multiple distinct episodes of wall collapse at different times. Galaxies from one old wall should look slightly different from galaxies from another. Their chemical compositions, their ages, their orbital motions inside the void should all carry information about which wall they came from and when that wall broke down. Testing that prediction requires more detailed surveys than currently exist, but the tools to do it are coming. And when they arrive, the tube of galaxies inside the Boötes void may turn out to be one of the most detailed records of cosmic merger history that we have ever found. Somewhere deeper in this story is a question that the merger model raises but does not answer. If smaller voids merge into larger ones, and larger ones keep merging into even larger ones, where does the process stop? Is there a maximum size that a void can reach? Or does the universe keep building emptiness at larger and larger scales without limit? When Robert Kirshner's team looked at their data in 1981, they did not immediately publish a paper with a dramatic name. Scientists rarely work that way. They checked their data, they rechecked it. They asked whether instrumental error or survey bias could explain the blank region in their galaxy maps. The answer was no. The blank region was real. And when colleagues heard about it informally, before any formal publication, the phrase that stuck was simple and direct: the great nothing. 2 words that captured what the data showed without any scientific qualification or softening. The name traveled fast in astronomical circles, a region of space so empty it looked, in the redshift maps, like someone had simply removed a chunk of the universe and left only dark space in its place. The formal name came from its location in the sky, the direction of the constellation Boötes. But the informal name, the Great Nothing, carries a weight that the formal one does not. Calling something nothing is a strong claim, and the claim felt justified at the time because the void was so much more extreme than anything astronomers had encountered before. Previous surveys had found smaller voids, gaps in the galaxy distribution that could be explained as normal features of the cosmic web. The Boötes void was an order of magnitude larger than those. An order of magnitude means roughly 10 times as large. The Boötes void was not slightly bigger than previous voids. It was dramatically bigger. Big enough that the standard models of the time had difficulty producing it through normal structure formation. Big enough that a serious fraction of the astronomical community initially suspected an error in the data. The name also matters because of what it does to the imagination. Nothing is a concept humans struggle with. True nothingness is philosophically and physically difficult to process. The void is not truly nothing, as we have covered, but the name locked in a public perception of the Boötes void as a place where physics might have failed. where the universe produced an absence so large it defied normal explanation. That perception, though exaggerated, has proven useful. The Boötes void became famous enough to attract sustained scientific attention. Astronomers who might have moved on to other targets kept returning to it, producing follow-up surveys, better measurements, and eventually, the more nuanced understanding of void formation we have today. The dramatic nickname kept the region visible in the scientific conversation. It also introduced a wider audience to a part of cosmology that rarely gets attention: the large-scale structure of the universe and the physics of how matter organizes itself across the longest distances. Most people know about galaxies and black holes. Far fewer know that the universe has a web structure, or that voids occupy the majority of its volume. The Great Nothing fixed that, at least a little. Now, consider what the name obscures. The void is not uniform. It has internal structure. It has 60 galaxies. It has a tube-shaped distribution of matter. And it may be the merged product of a long and complex history involving multiple smaller voids. The reality is richer than a name meaning emptiness can contain. A place called nothing turns out to be one of the most information-dense regions of the observable universe, precisely because understanding why it is almost empty tells us something profound about how the universe builds everything else. And the next layer of that story involves a force that does not get nearly enough attention when people talk about voids. When headlines say the Boötes void is spreading, the picture most people form is something like a stain expanding across a tablecloth, an absence growing, swallowing nearby galaxies, creeping outward through space like a slow disaster. The real process is more subtle, and in some ways, stranger. A void does grow over time, but it does not grow by consuming galaxies the way a black hole consumes matter. It grows because matter at its edges chooses, under the influence of gravity, to leave. The galaxies near the boundary of the void do not get pulled into the void. They get pulled away from it, toward the denser filaments that surround the void on the outside. Here is the mechanics. The boundary of a void is the transition zone between low-density interior and higher-density exterior. Galaxies sitting right at that boundary feel gravitational pull from two directions. The sparse void interior pulls them inward, weakly. The dense filaments and clusters outside pull them outward, more strongly. Over billions of years, most of those boundary galaxies migrate outward toward the filament. As they leave, the boundary of the void shifts. The region where galaxy density drops below average extends slightly further into what used to be filament territory. The void has effectively grown because the line dividing underdense from average density has moved outward. This is what spreading means in cosmology. The void grows emptier at its edges as matter exits toward denser regions. The emptiness deepens at the interior as fewer and fewer galaxies remain, and the overall volume of the underdense region increases over time. None of this happens at any speed a human could observe. The process unfolds across tens and hundreds of millions of years. Individual galaxies do not visibly drift away from the void boundary during any human lifetime or any civilization's recorded history. The spreading is geological in pace, but spread it does. There is also a second mechanism that contributes: the expansion of the universe itself. Space is expanding everywhere, stretching the distances between all objects that are not gravitationally bound to each other. Inside a dense cluster, the gravity binding galaxies together is strong enough to resist the expansion. Galaxies in a cluster do not drift apart. Inside a void, where gravity is weak and galaxies are far apart, the expansion of space has more leverage. The already enormous distances between galaxies in the void get stretched further by cosmic expansion. This means the Boötes void gets larger in two ways at once. Matter drains outward through gravitational dynamics, and space itself stretches the interior distances further. Both processes are real, both are slow, and both are unstoppable. The combined result is a void that has been growing since it first formed and will keep growing for as long as the universe continues to expand. The 60 galaxies inside it already spread impossibly thin, will grow farther apart over cosmic time. The void will be emptier in 10 billion years than it is today. And farther in the future, if the expansion of the universe continues to accelerate, some of those 60 galaxies may drift beyond each other's visible horizon. At that point, a civilization inside the void would be truly alone, unable to detect any other galaxy at any distance, surrounded by a void that, to their instruments, would appear to be everything. Every galaxy in the universe floats inside a halo of something invisible. Scientists call it dark matter. It produces no light, emits no radiation, and interacts with ordinary matter only through gravity. We cannot see it, photograph it, or directly detect it with any instrument currently available. We know it exists because of what it does to the things around it. Dark matter outweighs ordinary matter in the universe by a factor of roughly 5 to 1. For every pound of atoms, stars, gas, and planets in the universe, there are 5 pounds of dark matter. It fills the cosmic web. It forms the invisible skeleton that ordinary matter follows when building galaxies, clusters, and filaments. Without dark matter, the cosmic web would not exist in its current form. The gravity from ordinary matter alone would not be strong enough to build structures the size of galaxy clusters or the filaments that connect them. Inside voids, dark matter is present too, just less of it. Because voids form in regions that started with less matter overall, they also started with less dark matter. As ordinary matter drained from the void toward the surrounding filaments, dark matter drained with it, following the same gravitational gradients. The interior of the Boötes void has both fewer galaxies and less dark matter than the cosmic average, but the dark matter that remains inside the void still has effects. The 60 galaxies that orbit through the Boötes void each carry their own dark matter halos. Those halos are smaller than the halos of galaxies living in dense clusters because the void environment provides less material for them to grow. But they still influence how those galaxies move, how they retain or lose gas, and whether they can still form stars at any meaningful rate. The dark matter distribution inside the void also shapes what happens at the void's boundary. Where the void's underdense interior meets the surrounding cosmic web, dark matter builds up into a shell-like structure at the edge. This shell is not dramatic or abrupt. It is a gradual increase in dark matter density that mirrors the increase in galaxy density at the void's boundary. But it creates a kind of scaffolding for the material at the void's edge, holding the boundary galaxies in place while the interior continues to drain. Some cosmologists have proposed using voids precisely because of their simple, dark matter environment. In a dense cluster, dark matter from dozens of different halos overlaps and interacts in complicated ways. In a void, the dark matter distribution is cleaner and more spread out. This makes voids useful laboratories for studying how dark matter behaves when it is not crowded, which tells scientists things about its properties that they cannot easily learn from studying crowded regions. The Boötes void, as the most extreme underdense region on record, represents the cleanest laboratory of all, a place where dark matter has been removed to the maximum possible degree while still leaving a handful of galaxy-sized halos as traces. What happens at the void's interior boundary, where even the dark matter scaffolding grows thin, is a territory that no survey has yet mapped with precision. The instruments needed to track dark matter distribution inside the void at that level of detail are still being built. When they come online, the interior of the Great Nothing will stop being blank. It will become one of the most detailed dark matter maps ever produced. And that map will likely reveal something that changes how we think about what the void really contains. Gravity pulls things together, everyone knows that. But the universe is also expanding, and that expansion is accelerating. Something is pushing space apart faster and faster over time. Scientists call it dark energy. They do not know what it is. They know it exists because the universe's expansion is speeding up when it should be slowing down. Without dark energy, gravity should be winning. The mutual attraction between all the matter in the universe should be gradually pulling everything together, slowing the expansion down over time, the way air resistance slows a thrown ball. Instead, the universe's expansion is getting faster. Something is overpowering gravity on the largest scales. Dark energy is distributed evenly through all of space. It does not pile up in dense regions the way matter does. It fills the voids just as much as it fills the filaments. In fact, because voids have less matter pulling in the opposite direction, dark energy's effect is relatively stronger inside a void than in a dense cluster. What this means for the Boötes void is that the expansion of space inside the void is slightly more pronounced than the cosmic average. The already enormous distances between the void's interior galaxies get stretched by both dark energy-driven expansion and the gravitational drainage of matter. The two effects push in the same direction, deepening the void and widening the distances inside it simultaneously. On a cosmic scale, dark energy is also changing the structure of the void's boundary. As the universe accelerates, the large-scale structure of the cosmic web freezes. In the far future, the rate of expansion will outpace the rate at which gravity can move matter from one place to another. When that happens, the drainage process that currently empties voids and builds filaments will slow dramatically. The cosmic web will stop evolving. Voids will stop growing through drainage, and dark energy will continue to stretch the space inside them, pulling the remaining interior galaxies apart even as no new material enters from outside. The Boötes void will survive into the far future as an even more extreme version of itself, emptier, wider, more isolated from the surrounding structure. But dark energy matters to the story of the Boötes void for another reason beyond what it does to the void over time. It matters because the Boötes void is one of the tools scientists use to measure dark energy itself. The relationship between void size, void shape, and the rate of cosmic expansion carries information about how dark energy behaves. A universe with more dark energy would produce voids that grow differently from a universe with less. By mapping the properties of voids at different distances from us, which means different points in cosmic time, astronomers can trace how the expansion rate has changed over billions of years. That history is a fingerprint of dark energy's nature. Voids are uniquely well suited to this measurement. Because they are simple, a cluster of galaxies is complicated. Hundreds of gravitational interactions, gas dynamics, feedback from black holes, all layered on top of each other. A void has almost none of that complexity. The physics inside a void is dominated by the large-scale expansion of space and the gentle outward drainage of matter. Two effects: relatively clean, relatively measurable. The Boötes void, as the largest and most extreme void nearby, carries the strongest signal. What its shape, its depth of underdensity, and its evolution over time tell us about dark energy could help clarify one of the deepest unsolved problems in all of physics. Science is built on models. A model is a description of how reality works. You build one by collecting observations, finding patterns, and writing equations that reproduce those patterns. Then you test the model by using it to predict things you have not yet observed. If the predictions match reality, the model holds. If they do not, the model needs work. The standard model of cosmology, called lambda CDM, is the most tested and successful model in the history of science. Lambda stands for dark energy. CDM stands for cold dark matter. The model describes how the universe began, how it expanded, how matter clustered into galaxies and filaments, and how voids formed in the spaces between them. Its predictions match observations across an enormous range of scales and cosmic history. The Boötes void tests it. When you run the lambda CDM model forward from the early universe, generating simulated universes and looking for voids, the simulations produce voids of various sizes. Most are small, some are medium, a few are large. The Boötes void, at 300 million light-years across, sits at or beyond the upper end of what the model predicts should form naturally. Finding one void this large is possible within the model. Statistics allow for rare events. A simulation run enough times will occasionally produce something close to the Boötes void by chance. But the probability is low. And the probability matters, because if you find many structures at this scale, the rarity argument breaks down. The model cannot use luck as an explanation if the universe consistently produces surprises of that magnitude. This is where the Boötes void connects to a larger debate in cosmology. Astronomers have found several large-scale structures in the universe that push the boundaries of what lambda CDM comfortably predicts. The Boötes void is one. The Hercules Corona Borealis Great Wall is another. The cold spot in the cosmic microwave background is a third. Each one, individually, can be explained as a statistical outlier. Together, they raise a question. Are these structures the rare tale of a normal distribution, or are they evidence of something missing from the model? Most cosmologists currently favor the first answer. The model is working, and these structures are simply rare. But a growing minority argues that the accumulation of large anomalies deserves a more serious response. A model that keeps needing luck to explain its most extreme predictions should be examined carefully. The Boötes void sits at the center of that debate. It is not proof that lambda CDM is wrong. It is a stress test, a place where the model's predictions grow thin and uncertain. If future surveys find the void's true size and shape match the model's most generous estimates, the model survives intact. If the void turns out to be larger than current measurements suggest, or if its internal structure reveals something that the model cannot produce even in rare runs, the model will need revision. Science welcomes that possibility. A model that cannot be tested is not science. The Boötes void is a test, and the outcome of that test, still years away from resolution, will tell us whether our best description of the universe is complete or whether something fundamental is missing. What that missing piece might be, and where the clues to finding it are hiding, is the subject of a debate that extends far beyond the Boötes void into the deepest open questions in all of cosmology. The number 60 is not certain. Every time a major survey maps the interior of the Boötes void, it produces a count of galaxies detected with confidence. 60 is the number most commonly cited, based on the surveys that have been published. But every survey has a detection limit. Below a certain brightness, galaxies become invisible to the instruments in use. A galaxy too faint, too small, or too redshifted for a given telescope simply does not show up in the data. The 60 galaxies inside the Boötes void are the galaxies bright enough and large enough to be detected by the surveys conducted so far. The question is, how many more might be hiding below that threshold? Dwarf galaxies are the most likely candidates. These are small, dim collections of stars and gas, far less luminous than the Milky Way or the spiral galaxies you see in most astronomy images. The universe contains enormous numbers of them. In dense galaxy clusters, they are common, but they are also difficult to detect at large distances because their low brightness makes them easy to miss. The Boötes void sits between roughly 700 million and 1 billion light-years from Earth, depending on which edge you are measuring to. At that distance, a dwarf galaxy might be too faint for current survey telescopes to pick up, even with long exposures. Some estimates suggest the true galaxy count inside the void, including all dwarf galaxies and other low-luminosity systems, could be several times higher than 60. A few hundred is not an unreasonable guess if you include everything current instruments cannot yet see. Even so, the expected count is still 2,000. A few hundred would still represent a 90% or greater deficit. The void's dramatic underdensity survives even the most optimistic upward revision of the true galaxy count. But the missing galaxies matter for a different reason beyond just the count. The spatial distribution of those hidden galaxies could contain information about the void's internal structure that the current data is missing. If dwarf galaxies are scattered randomly through the void's interior, that would suggest the void's history is simpler than the merger hypothesis requires. If they are concentrated in or around the tube of bright galaxies already identified, it would strengthen the case that the tube marks an old boundary. The tools to answer that question are arriving. Newer telescopes under construction will push the detection limit to far fainter objects at the void's distance. Sky surveys planned for the next decade will cover the entire Boötes void with sensitivity high enough to detect systems significantly smaller and dimmer than anything currently catalogued there. When those surveys run, the interior of the void will stop being a mystery with 60 known points of light. It will become a detailed three-dimensional map of every galaxy, dwarf galaxy, and stellar stream that survived the drainage of billions of years. That map will be a test of the merger hypothesis. It will be a test of how galaxy formation works in extremely low-density environments. And it will be a test of whether the void's boundary is where current measurements place it, or whether the underdense region extends further in some directions than current data shows. Until then, the 60 known galaxies are the best evidence we have. And in the absence of complete data, the tube shape they form is the most powerful structural clue available. That clue points directly at the void's interior, where something far more unexpected may be waiting. The universe is expanding. Every major observatory on Earth and in orbit has confirmed this. Galaxies are moving away from us, and the farther away they are, the faster they recede. That much is settled. The debate is over exactly how fast. This debate has a name in cosmology: the Hubble tension. Two different methods of measuring the universe's expansion rate keep producing two different answers. One method uses the cosmic microwave background, the ancient light from the early universe, to calculate how fast space should be expanding today based on the physics of the early cosmos. The other method measures distances and speeds of nearby galaxies directly. The two answers disagree by enough to matter. Scientists have checked both methods repeatedly. The disagreement persists. Cosmic voids offer a third method. Here is how it works. When light travels through a void, it has to climb out of the void's gravitational environment on the far side. A void has less mass than average, so the gravitational well it creates is shallower than average. Light crossing a void gains a tiny amount of energy entering it and loses a tiny amount leaving it. In a universe where the expansion rate is constant, those two effects cancel out perfectly. The light arrives unchanged. But the universe is not expanding at a constant rate. Dark energy is accelerating the expansion. During the time it takes light to cross a void, the void itself grows slightly larger due to expansion. The light exits a slightly bigger void than the one it entered. The energy gain and energy loss no longer cancel. The light arrives with a faint but measurable fingerprint of the expansion that happened while it was crossing. That fingerprint is called the integrated Sachs-Wolf effect. Measuring it across multiple voids at different distances from us builds a picture of how the expansion rate has changed over cosmic time. Each void contributes a data point. The largest and most precisely mapped voids contribute the strongest signal. The Boötes void, as one of the largest known supervoids within a reasonably close distance to our own region of the universe, produces a stronger signal than smaller voids. Astronomers have included it in analyses aimed at measuring how the expansion rate differs from what the early universe models predict. The results are not yet precise enough to settle the Hubble tension, but they are precise enough to constrain the possibilities. The power of using voids for this measurement comes from their simplicity. A dense galaxy cluster is a gravitational environment so complex that calculating the expected light energy behavior requires accounting for hundreds of overlapping effects. A void is almost featureless. The dominant physics is the large-scale geometry of space, and the rate at which that geometry is changing. Fewer complications mean cleaner data. Cleaner data means tighter constraints on the expansion rate. As survey technology improves, and astronomers map more voids with greater precision, the void-based measurement of cosmic expansion will sharpen. The Boötes void will remain one of the key reference points in that effort, a giant calibration tool hanging in space, encoding the history of cosmic expansion in the subtle energy shifts of every photon that passes through it. The fact that a nearly empty region of space serves as one of our most powerful tools for understanding the universe's fundamental behavior is one of the more unexpected turns in the story of the Great Nothing. The Boötes void does not exist in isolation. It sits inside a framework so large that the void itself, 300 million light-years across, looks like a single gap in a structure that stretches across the entire observable universe. That framework is the cosmic web. Think of the web as a three-dimensional city, built without any architect. In a real city, buildings cluster around transportation hubs, roads connect hubs, neighborhoods form where roads intersect. Empty lots fill the spaces between buildings. Scale that up by a factor so large it loses all meaning in everyday terms, and you get the cosmic web. Galaxy clusters at the major intersections. Filaments of galaxies stretching along the roads. Flat sheets of galaxies forming the neighborhoods. And voids in the empty lots between all of it. The filaments are where most galaxies live. A single filament can stretch hundreds of millions of light years and contain thousands of galaxies strung along its length like lights on a wire. Where two or more filaments converge, you find a galaxy cluster, a dense, hot, gravitationally bound collection of hundreds or thousands of galaxies crowded into a space just a few million light years across. The most massive clusters contain more total matter than 1,000 Milky Way galaxies combined. The walls are the flattest large-scale structures, where two voids sit back to back, separated by a flat sheet of galaxies. That sheet is a cosmic wall. Some walls span distances that dwarf even the largest filaments. The Sloan Great Wall, identified in the early 2000s, stretches about 1.5 billion light-years across. At the time of its discovery, it was the largest known structure in the universe. Then came even larger finds. The Hercules Corona Borealis, Great Wall, identified in the 2010s, spans roughly 10 billion light-years. That structure is so large that light crossing it from one end to the other takes longer than the current age of the universe. Some cosmologists argue that structures that large should not exist under standard models of cosmic formation, making them, like the Boötes void, potential stress tests for lambda CDM. The Boötes void sits near the boundary between several filaments and walls. Its edges are defined by the filaments surrounding it. The 60 interior galaxies are completely cut off from those filaments by the void's enormous empty interior. A galaxy on one side of the void cannot gravitationally interact with a galaxy on the other side in any meaningful way on current cosmic timescales. The void acts as an insulating barrier between the structures on either side of it. This matters for understanding the cosmic web as a whole. Voids do not just fill space. They separate regions of the web from each other. They limit which galaxy clusters can exchange matter with which filaments. They shape the overall connectivity of the cosmic structure. A universe with fewer or smaller voids would have a much more interconnected web where matter could flow more freely between all parts of the structure. The Boötes void is one of the largest of these separators, and it has been growing for nearly 14 billion years. Every year, the separation it creates between the structures on its opposite sides grows slightly wider. The web it sits within is slowly being partitioned into more isolated regions by the voids between its strands. And the Boötes void is far from the largest empty region astronomers have encountered. There are structures out there that make it look almost cozy. In 2004, a team of astronomers studying the cosmic microwave background found something that did not belong. A region of the sky, roughly 14 degrees across, where the ancient light from the early universe was colder than the surrounding areas by a small but measurable amount. They called it the cold spot. The cosmic microwave background fills the entire sky with a near-uniform glow of ancient radiation. It is the leftover heat from when the universe first became transparent, about 380,000 years after the Big Bang. On average, this glow is almost perfectly smooth. Temperature variations are tiny, fractions of a percent, but those tiny variations carry enormous information about the structure of the early universe. The cold spot is colder than it should be. The temperature dip is small in absolute terms, but far larger than the standard model predicts should happen by chance at that particular angular scale. Scientists ran the statistics. The probability of the cold spot appearing randomly in a standard lambda CDM universe came out very low, low enough to attract serious attention. Several explanations were proposed. One of the most persistent is a supervoid. If an enormous, underdense region sits between us and the cold spot, the light from the cosmic microwave background passing through that void would lose energy, arriving at our telescopes slightly cooler than light that took a different path. The size and depth of the void required to produce the observed temperature dip would make it one of the largest structures ever found. A supervoid in the right location was identified. Scientists found a region of low galaxy density in the direction of the cold spot between 1 and 3 billion light-years away. The void is real. The debate is whether it is deep enough and large enough to fully explain the temperature dip, or whether it only accounts for part of the effect. If the void explains the cold spot entirely, then the cold spot is an extreme but natural feature of a universe filled with voids of all sizes. If the void is insufficient, something else contributed to the cooling. What that something else might be ranges from the mundane to the extraordinary. Instrument noise, statistical coincidence, a massive collision between our universe and another one during its earliest moments. That last possibility, a collision with a parallel universe, remains highly speculative with no direct supporting evidence. But it has captured public attention because it represents the most dramatic possible explanation. A scar left by a collision with another universe, imprinted on the oldest light in the cosmos. The connection to the Boötes void is structural. Both are supervoids. Both sit in a universe whose standard model struggles to comfortably accommodate their existence at their current scales. Both raise the same fundamental question. Are these structures the expected extremes of normal cosmic variance? Or do they point toward physics that the standard model has not yet captured? The cold spot and Boötes are not the same structure. They sit in completely different regions of the sky, at different distances. But they are part of the same conversation. A universe that produces multiple anomalously large voids deserves careful examination, and there is a third void in that conversation, one that is harder to dismiss than either of the others, because it may surround the very galaxy we call home. In 2013, astronomers found evidence that our galaxy, the Milky Way, may sit inside a void, a large region of space surrounding us, extending roughly 1 billion light-years in every direction, appears to have a lower galaxy density than the universe average. Researchers named it the KBC void, after the initials of the team members who identified it. The KBC void, if real at the scale currently estimated, would be one of the largest underdense regions ever identified, far larger than the Boötes void in total volume. Our galaxy would sit roughly at its center, inside an enormous bubble of relative emptiness, surrounded by a denser shell of galaxy clusters and filaments at its boundary. This matters for several reasons. First, living inside a void would affect how we measure the universe's expansion rate. Galaxies inside a void move away from each other slightly differently than galaxies in denser regions. If the Hubble tension, the disagreement between different measurements of how fast the universe is expanding, has any connection to our local environment, the KBC void could be part of the explanation. A universe measured from inside a void might systematically produce a different expansion rate than the same universe measured from a denser region. Some cosmologists have proposed exactly this. Our measurement of the local expansion rate might be skewed by the fact that we sit inside an underdense environment. If the KBC void is real and as large as estimated, it could account for some or all of the discrepancy between the early universe and local measurements of expansion. The debate over the KBC void is less settled than the debate over Boötes. Some follow-up surveys find evidence supporting the underdensity. Others find a smaller or less extreme effect. The void's existence at a modest level is reasonably well supported. Its size, and whether it is large enough to meaningfully affect cosmological measurements, is still contested. Comparing the KBC void to the Boötes void highlights something important about how voids are detected. Boötes was found by looking at a distant region of the sky and noting the absence of galaxies in three-dimensional survey data. The KBC void is harder to measure because we are inside it. Measuring the density of your own environment requires comparing what you observe in all directions to what the universe looks like on average. That comparison is complicated by the fact that the average itself is partly defined by your local sample. If you have ever tried to judge whether your neighborhood is unusual by only ever having lived in it, you understand the difficulty. You need to look outward and compare. For the KBC void, that means mapping galaxy density across enormous distances in every direction and comparing to independent measures of the cosmic average. That process is ongoing. What the KBC void means for the Boötes void is context. We may be void dwellers studying another void, two enormous empty regions, one containing us and one sitting hundreds of millions of light years away, both pushing the edges of what standard cosmology expects. Both part of a universe that produces emptiness at scales that still make scientists uncomfortable. And between us and the Boötes void, the cosmic web stretches through spaces filled with structures stranger than either void. Stand outside on a clear night, far from city lights. Give your eyes 30 minutes to adjust. The sky fills with stars, planets, and the soft arc of the Milky Way. On the best nights, you can make out the faint smudge of the Andromeda galaxy with the naked eye, 2.5 million light-years away. The sky feels crowded with light. That experience depends entirely on where in the universe you live. If your planet orbited a star inside a dense galaxy cluster, the night sky would be spectacular beyond anything a human has ever seen. Dozens of nearby galaxies visible to the naked eye, each a different shape and brightness. Star-forming regions glowing pink and blue. The diffuse light of thousands of galaxies overlapping at the sky's horizon. A night sky so bright that true darkness might never come. If your planet orbited a star inside the Boötes void, the experience would be the opposite. Your own galaxy would still be there, of course. You would still see the Milky Way's disk arching overhead if you lived far enough from its center. Your star's immediate neighborhood would have other stars. The sky would not be completely dark, but look outward, beyond your galaxy, and you would find almost nothing. The nearest large galaxy neighbor outside the void would be hundreds of millions of light-years away. At that distance, even a galaxy containing hundreds of billions of stars would appear as a faint point of light, requiring a powerful telescope to detect. The cosmic web's bright filaments and clusters, which form much of the diffuse background glow astronomers see when they point instruments at the deep sky, would be so far away they would barely register. A civilization inside the Boötes void would face a profound and strange challenge. They would look at the universe and see almost nothing beyond their own galaxy. No nearby neighbor galaxies to study. No clusters to observe at manageable distances. The entire observable universe, as seen from inside the void, would be nearly blank in most directions. Their cosmology would develop very differently from ours. They might spend centuries debating whether other galaxies exist at all. The evidence for large-scale structure would be sparse and ambiguous. The idea of a cosmic web filled with galaxy clusters would require faith in faint signals at the extreme edge of detection. They might conclude, for a very long time, that their galaxy was alone. When they finally developed instruments powerful enough to detect the faint smudges at the void's edge, the discovery would be genuinely earth-shaking. An entire universe filled with structure, completely hidden by distance and emptiness, suddenly revealed. The shock of that discovery would be comparable to the moment Galileo pointed a telescope at the sky and saw that the universe was not what everyone assumed. We face a version of this problem ourselves, though less extreme. Our local cosmic environment, possibly the KBC void, affects what we can see and measure. The cosmic perspective we have developed is shaped by where in the universe we happen to be. Different observers in different cosmic environments would build different pictures of the same reality. The Boötes void forces that realization into sharp focus. The universe does not look the same from everywhere inside it. Location matters. And for any civilization unlucky enough to form inside the Great Nothing, the universe would have seemed, for a very long time, unimaginably empty and truly alone. Imagine a civilization that developed science and technology roughly in line with our own history. They built telescopes. They launched satellites. They developed mathematics and physics capable of describing the cosmos. But they lived inside the Boötes void. Their journey toward understanding the universe would hit walls that ours never did. Start with the problem of cosmic distance measurement. We learned how to measure cosmic distances partly by studying variable stars called Cepheids in nearby galaxies. We measured distances to galaxy clusters by studying supernovas in them. We calibrated our distance scale against a ladder of nearby reference points. The rungs of that ladder reach from our solar system to our galaxy, to the local group, to the nearest clusters, and eventually to the distant universe. A civilization inside the Boötes void would have trouble building many of those rungs. The nearest galaxy clusters sit at the void's edge, hundreds of millions of light years away. Studying Cepheids at that distance requires instruments far more powerful than the ones that allowed us to take our first steps up the distance ladder. With no nearby galaxies to use as calibration, their distance measurements would carry larger errors, especially in the early stages of their science. Next, consider galaxy formation. Much of what we know about how galaxies form and evolve comes from comparing galaxies at different distances. Distant galaxies are younger, because light takes time to travel. Nearby galaxies are older. Comparing the two reveals how galaxies change over billions of years. A civilization inside the Boötes void has 60 neighbors to study. The statistical power of 60 objects is dramatically lower than the statistical power of thousands. Their models of galaxy evolution would develop more slowly and with more uncertainty. The large-scale structure of the universe would be the hardest thing to grasp. We discovered the cosmic web with its filaments, walls, and voids through redshift surveys that mapped millions of galaxies across hundreds of millions of light years. A civilization inside the void would need to survey to much greater distances before encountering enough galaxies to reveal the web's pattern. Their surveys would require more powerful instruments and longer timescales to reach the same understanding. But here is the twist. Once they achieved that level of observation, the discovery of the cosmic web would be even more stunning for them than it was for us. From their position in the void, they would first detect the faint, distant boundary of their own void. Then, just beyond that boundary, the cosmic web would appear in startling contrast, an almost empty interior suddenly giving way to dense filaments and clusters at the edge of their detectable universe. They would understand their own void by its contrast with everything surrounding it. The structure of the cosmos would announce itself at the void's boundary. Their cosmology would be built from the outside in, where ours developed by looking outward from a position already inside the web's structure. Theirs would develop by detecting the web from the inside of a hole in it. Same universe. Completely different journey to understanding it. That difference in perspective is not just a thought experiment. It is a reminder that scientific understanding is always shaped by observational position. Our picture of the cosmos reflects where we happen to be. What we call the standard model is built on evidence gathered from one location in one galaxy, on one side of one filament of the cosmic web. The Boötes void is a mirror that reflects the contingency of everything we know. Neutrinos are among the strangest particles in the universe. They have almost no mass. They interact with almost nothing. Billions of them pass through your body every second without touching a single atom. They are produced in enormous quantities by the sun, by supernovas, by radioactive decay, and by the Big Bang itself. The universe is saturated with them. They are also one of the least appreciated ingredients in the recipe for cosmic structure. In the early universe, neutrinos were everywhere, and they moved fast, close to the speed of light. Because they moved so quickly, they could not be captured by the gravitational pull of the small clumps of matter forming in the early cosmos. Any region that started gathering matter and building up a density enhancement had trouble holding on to neutrinos. The neutrinos streaked through and away, carrying their tiny mass out of the forming structure. This matters because mass drives gravity. A clump of matter with more mass pulls harder on its surroundings. If neutrinos escape from forming density peaks, those peaks grow more slowly. The pattern of structure that develops, the arrangement of filaments and voids, carries the signature of how much neutrino mass exists and how fast those neutrinos moved in the early universe. The precise mass of neutrinos is one of the open problems in particle physics. Laboratory experiments have set upper limits on the mass, but have not yet pinned down the exact value. Cosmological observations offer a different route to the answer. The large-scale structure of the universe, including the sizes and shapes of voids, carries information about the neutrino mass imprinted during structure formation. Voids are particularly sensitive to this. In regions where matter is trying to drain away and leave a void, neutrinos that escape the draining process help determine how quickly the void empties and how large it can grow. A universe with heavier neutrinos produces a slightly different void distribution than a universe with lighter ones. The difference is subtle, but detectable in principle with precise enough measurements. The Boötes void, as one of the most extreme voids in the observable universe, sits at the edge of what the neutrino mass allows cosmic structure to produce. If neutrinos were significantly heavier than current limits suggest, the void should not be this large. Heavier neutrinos would have slowed structure formation in a way that prevents the most extreme voids from developing. The existence of the Boötes void at its current scale is consistent with the neutrino mass range that particle physics experiments currently favor. That consistency is a small but real piece of evidence connecting the largest empty space ever found to the smallest known massive particles in existence. The void encodes particle physics. Reading it precisely enough could help resolve a question that laboratory experiments have not yet answered. This is what makes the Boötes void genuinely important beyond its size and strangeness. It is a measurement tool. Every property of the void, its size, its depth of underdensity, its shape, its internal galaxy distribution, contains encoded information about the physics that shaped the universe from its earliest moments. The particle and the void are linked by 14 billion years of cosmic evolution, and between them, they hold the answer to questions that neither particle physics nor cosmology can solve alone. The Standard Model of cosmology is a remarkable achievement. It describes the universe's origin, expansion, and structure with a precision that would have seemed impossible a century ago. When you run its equations forward from the Big Bang, the universe that emerges matches what telescopes see with startling accuracy: galaxy clustering, the cosmic microwave background, the abundance of light elements, the large-scale structure of the web, all of it aligns. And yet, a small but serious group of cosmologists argues that the model carries tensions it cannot absorb indefinitely. The Hubble tension is the most discussed. The expansion rate measured locally disagrees with the expansion rate calculated from the early universe. The gap has survived years of data collection and instrument checks. It is real enough that theorists have proposed dozens of possible solutions: new light particles in the early universe, modified dark energy, extra-relativistic species, small-scale modifications to the physics of recombination. None of them has one consensus. The Boötes void adds a quieter but related concern. The Standard Model produces voids, but producing one this large through straightforward structure formation is at the edge of comfortable probability. Add the cold spot, add the Hercules Corona Borealis Great Wall, add the KBC void, and the accumulation of structures sitting at the boundary of what standard physics comfortably predicts begins to feel like a pattern rather than a series of coincidences. Some physicists have proposed modifications to the Standard Model that would naturally produce more extreme voids. One class of proposals involves modifications to dark energy. Instead of a constant energy density filling space uniformly, Some models allow dark energy to vary slightly with time or position. A dark energy that behaved differently in the early universe could have accelerated structure formation in ways that naturally produce larger and emptier voids. Another proposal involves primordial features. The tiny density ripples from the early universe that seeded all structure might have had departures from a perfectly smooth statistical distribution. Local spikes, or dips in the density field, larger than the standard model predicts, could have seeded extreme structures like the Boötes void more naturally. A third category of proposals reaches further. Some theorists have explored whether the Boötes void scale could be connected to physics beyond the standard model entirely. Extra dimensions, modifications to gravity at large scales, or effects from the inflationary period that ended a fraction of a second after the Big Bang. These ideas range from conservative to speculative. None has clear supporting evidence from the void alone. The honest assessment, which most cosmologists would agree with, is that the Boötes void is unusual but almost certainly explainable within standard physics. Once the full statistical range of possible outcomes is properly accounted for, almost certainly is the phrase that keeps this conversation alive, because almost certainly is not the same as definitely, and science advances precisely in the space between those two positions. History shows that anomalies dismissed as unlikely but possible have sometimes turned out to be the first glimpse of something genuinely new. The Boötes void is almost certainly a stress test that the standard model will pass. The key word is almost. Galaxies form from gas. Enormous clouds of hydrogen and helium, the simplest elements forged in the Big Bang, collapse under gravity into dense cores that ignite as stars. Those stars heat surrounding gas. They forge heavier elements in their cores and blast those elements into space when they die. The enriched gas falls back, forms new stars, builds disks and bulges, and eventually, the collection of billions of stars, held together by gravity, becomes what we call a galaxy. That process depends critically on environment. In a dense galaxy cluster, gas clouds are constantly being disturbed. Galaxies pass close to each other, and their mutual gravity strips gas from outer regions. High-speed collisions between galaxy clusters heat the surrounding gas so intensely that it cannot cool down enough to collapse into stars. The environment is too energetic, too chaotic. Galaxy formation slows and eventually mostly stops in the densest cluster cores. Inside a cosmic void, the opposite problem applies. The environment is too quiet, too empty. Gas clouds in a void have almost no external triggers to start collapse. In dense regions, a nearby supernova blast can compress a gas cloud and kick off a new round of star formation. In the void, supernovas are rare. Interactions between galaxies are rare. The steady supply of cold gas falling in along filaments, which feeds star formation in galaxies sitting on the cosmic web, is absent. The 60 galaxies inside the Boötes void have been forming stars at reduced rates compared to similar galaxies living in denser environments. Their star formation histories show that they were more active in the distant past, when the universe was younger and even void-dwelling galaxies had more raw material to work with. As the void deepened and the environment grew more isolated, star formation slowed. Some of the void's interior galaxies may have already exhausted the gas they can access. They will not form many new stars. They will age quietly, their light gradually redding as old stars burn out and new ones are born too rarely to compensate. In a few billion years, galaxies inside the Boötes void will look quite different from galaxies of similar age living in active filaments. The void is not killing its galaxies, it is aging them differently. This has implications for any planets inside the void. Star formation produces the heavy elements, carbon, oxygen, iron, silicon, that rocky planets and life as we know it are built from. A galaxy that forms fewer new stars produces fewer of those elements over time. The chemical enrichment of the galaxy slows. Planets forming around younger stars in such a galaxy would have access to less of the raw material required for rocky worlds. Life, as we understand it, requires certain chemical complexity. That complexity is built up over generations of stars, each cycle of birth and death enriching the surrounding gas with heavier elements. In a galaxy inside the Boötes void, where star formation has been running below average for billions of years, that enrichment happens more slowly. Whether life could arise at all in a void galaxy is unknown, but the chemical environment of a void galaxy is measurably different from ours, and that difference, subtle in the early universe, compounds over billions of years into something potentially significant for the question of where in the cosmos complexity can emerge. The void is not just an empty space, it is a different kind of universe, running by the same rules but shaped by its isolation into something distinct from the cosmos we call home. The tube of galaxies running through the Boötes void's interior is the most scientifically underappreciated feature of the entire structure. Most descriptions of the void focus on the emptiness, the size, the missing galaxies. The tube gets a footnote. That is backwards. The tube is a fossil record. In geology, when two rock layers of different ages press against each other along a fault line, the boundary between them preserves information about the history of movement in the Earth's crust. The boundary is not random. It reflects the shape of the geological event that created it. Geologists read faults to understand what happened millions of years before any human watched. The tube of galaxies inside the Boötes void is a cosmic fault line. It marks where two or more older, smaller voids once met and merged. The galaxies sitting along the tube are the survivors of the wall that used to separate those smaller voids. They are the last material trace of a boundary that no longer exists as a boundary. When two voids merge, the process is not instantaneous. The wall between them, a region of slightly higher galaxy density that separated the two underdense regions, takes time to drain. As matter leaves the wall toward the surrounding filaments, the wall thins. Galaxies that sat near the wall's edges drain away with the rest of the matter. But galaxies sitting deeper in the wall, farther from any filament and therefore exposed to weaker gravitational gradients, drain more slowly. By the time the wall fully collapses and the two voids become one, some of those deeper wall galaxies remain. They sit in the interior of the now merged void, stranded far from any filament, tracing the line of the old boundary. Their arrangement in the merged void reflects the orientation and shape of the wall they used to inhabit. The tube shape of the Boötes void's interior galaxies follows a specific orientation that cosmologists have compared to the positions of the surrounding filaments. The alignment makes sense geometrically if the tube marks the old boundary between two smaller voids that each developed in the gravitational shadow of the filaments now surrounding the merged structure. The old wall formed where it did because of the geometry of the surrounding web. The tube preserved that geometry. Reading the tube correctly requires knowing the three-dimensional positions of all the galaxies inside the void at high precision. Current surveys provide positions accurate enough to see the tube clearly, but not fine enough to map its internal structure in detail. Future instruments will map each galaxy's position, velocity, and age inside the void. That data will allow scientists to reconstruct which galaxies came from which part of the old wall and when the wall collapsed. That reconstruction will produce the first detailed timeline of void mergers in the observable universe. A history not of galaxies colliding, but of emptiness merging, of the great empty spaces of the cosmos, joining together over billions of years to produce one of the most extreme structures we have ever found. The tube is the key, and when we finally read it fully, the Boötes void will stop being a mystery of absence and become a record of process, a cosmic archive written in the positions of 60 lonely galaxies, waiting to be decoded. The golden age of void science is happening now. For most of the 20th century, mapping the large-scale structure of the universe meant small surveys covering narrow strips of sky, one galaxy at a time. The technology was limited. Surveys took years to complete and covered only small fractions of the observable universe. Understanding void structure required working with incomplete data and making assumptions to fill the gaps. That era is over. The Dark Energy Spectroscopic Instrument, installed at a telescope in Arizona, began its main survey in 2021. It is designed to measure the positions and distances of approximately 40 million galaxies and quasars across roughly one-third of the sky. By the end of its 5-year survey, it will produce the most detailed three-dimensional map of the universe ever assembled. Every void, filament, and cluster in its coverage area will be charted with a precision previous surveys could not approach. The Vera Rubin Observatory in Chile, now fully operational, surveys the southern sky with a camera so large it can photograph an area roughly 40 times the size of the full moon in a single image. It observes each patch of sky repeatedly over its 10-year survey, tracking how galaxies change over time and building a statistical record of structure formation across enormous volumes. The Euclid Space Telescope, launched in 2023, maps galaxies across more than one-third of the sky from orbit, free from the distortions that Earth's atmosphere introduces. It focuses particularly on measuring the shapes of galaxies distorted by gravitational lensing, which reveals the distribution of dark matter between us and them. Mapping dark matter in and around voids is one of its core scientific goals. These surveys are already returning data that changes the picture of void science. The early results from the Dark Energy Spectroscopic Instrument have produced void catalogs larger than any previously assembled. Researchers are identifying hundreds of new supervoids, mapping their properties, and comparing their distribution to the predictions of Lambda CDM. The comparison is ongoing. Preliminary results show general agreement, with some individual structures sitting at the edge of what the model predicts. The Boötes void falls partly inside and partly outside the coverage areas of these surveys, depending on which instrument is doing the observing. New data on its galaxy distribution and boundary properties are being gathered and analyzed. The picture of its interior is sharpening. The tube of galaxies that previous surveys identified at low resolution is being remapped with finer detail. Within the next decade, the question of whether the void's size and structure fit within standard cosmology will have a much more definitive answer. The surveys currently running will either confirm that Boötes is a rare but explainable product of normal physics, or they will reveal features that the standard model cannot accommodate. Either outcome advances science. The universe has always been stranger and richer than our models. Every time a better instrument looks deeper, it finds something that forces a revision. The Boötes void, mapped at the precision these new surveys allow, will almost certainly contain surprises. Whether those surprises are small adjustments or something larger is the question that keeps the people running these instruments working late. Empty things fill. Holes in sand get washed flat by waves. Low-pressure systems in the atmosphere draw in surrounding air. Gravity fills craters with debris over geological time. The universe, you might assume, would work the same way. Surely the Boötes void, sitting at lower density than its surroundings, should draw matter back in. Gravity is gravity. The void should fill itself. It does not work that way. And understanding why tells you something profound about the future of the universe. In a system where the only force is gravity, and the universe is not expanding, a low-density region would eventually draw matter back toward it. The slight pull of whatever mass remains inside the void would attract gas and galaxies from the boundary. Over time, the density inside would recover toward the average. The void would fill, slowly, but continuously. The universe is expanding, and the expansion is accelerating. Galaxies at the boundary of the Boötes void are already moving away from the void's interior. Some of them are moving away from each other fast enough that, in the far future, they will no longer be in causal contact. The distance between them will grow faster than light can cross it. At that point, gravity between them becomes irrelevant. The universe's expansion has stretched the space between them beyond the reach of any force. This is the fate that awaits the Boötes void. The boundary galaxies, already moving outward toward the surrounding filaments, will never return. The void will never fill. Instead, it will continue emptying as more of the matter near its edges drifts beyond the gravitational pull of the void's interior. Over the next few billion years, the void will grow slightly larger in volume and significantly emptier inside. The 60 interior galaxies will drift farther apart. Some may eventually cross each other's cosmological horizon, beyond the boundary where light can travel fast enough to connect them even given infinite time. In the very long term, as the universe's accelerating expansion continues, even the boundary between the void and the surrounding web will grow less meaningful. The filaments themselves will thin as matter stops being able to flow along them. The cosmic web will freeze, then fade. Individual galaxies, stripped of the cosmic environment that once connected them to each other, will age in isolation. The Boötes void, in a sense, is the preview. It shows what a large region of the universe looks like when the forces that build structure stop winning. When the balance tips from clustering to isolation, the void is already living in a future that the rest of the universe has not yet reached. The matter that left the void billions of years ago will never come back. The void is a one-way story, and it points in the direction the entire universe is heading. Slowly, over timescales no civilization will survive to observe. The future of the void is also the future of everything, just on different timescales. That realization, sitting quietly inside the great nothing, is one of the more unsettling pieces of knowledge that modern cosmology has produced. The Boötes void earned its fame by being one of the largest known voids in the universe. For a time, it was the largest. Then astronomers looked further, and the scale of the universe's empty spaces grew even harder to process. The cold spot supervoid, sitting between 1 and 3 billion light-years from Earth, spans a volume that dwarfs Boötes by a significant margin if current estimates are correct. Its boundaries are not as precisely defined as Boötes because it is much farther away and harder to map in detail, but the surveys that identified it place its extent well beyond 300 million light-years across. Then there is a structure called the Giant Arc. Discovered in 2021, it spans roughly 3.3 billion light-years across the sky. Unlike a void, the Giant Arc is a curved structure, a broad arc of galaxies, galaxy clusters, and gas sitting at a distance of about 9.5 billion light-years from Earth. Its existence raised immediate questions. A structure that large should not be able to form coherently under standard cosmology. The universe, at scales beyond roughly 1 billion light-years, should appear statistically uniform. Structures of 3 billion light-years should not exist. The debate over the Giant Arc is active. Some analyses confirm its significance. Others argue the pattern could emerge from a random distribution of galaxies at low statistical significance. The jury is still deliberating. The Hercules Corona Borealis Great Wall remains the largest known structure by most measurements. Spanning roughly 10 billion light-years, it sits at a distance of about 10 billion light-years from Earth. It was identified through the clustering of gamma-ray bursts, the most energetic explosions in the universe, which serve as tracers of galaxy distribution at extreme distances. A structure 10 billion light-years across, in a universe 93 billion light-years across, represents a significant fraction of the entire observable cosmos, concentrated in one feature. These structures, if confirmed at their reported sizes, push beyond the cosmological principle. That principle states that the universe, on large enough scales, looks the same in every direction and from every location, smooth, homogeneous. If structures exist at scales of billions of light-years, the universe is still lumpy at those scales. The smooth average appears only at even larger scales, if it appears at all within the observable universe. This does not prove the cosmological principle is wrong, but it does mean the scale at which the universe becomes smooth is larger than many earlier estimates assumed, and a universe that stays structured at larger scales has a different statistical fingerprint than one that smooths out quickly. Both versions are consistent with the Big Bang and with dark energy and dark matter. The difference is in the details of the initial conditions and the physics of structure formation. The Boötes void, once a record holder in the catalogue of extreme cosmic structures, now sits in a growing list of anomalously large features. Each new addition to that list shifts the conversation slightly further toward the question of whether the standard model is missing something, and each new survey brings us closer to the data that will answer that question definitively. What sits at the boundaries of these larger structures, where the emptiness of a supervoid meets the dense shell of matter surrounding it, is one of the most active areas of observational cosmology today. The boundary of the Boötes void is not a wall. There is no sharp line where empty space gives way to full space. The transition is gradual, stretched across tens of millions of light years, a slow thickening of the cosmic web as you move from the void's interior toward the surrounding filaments. But gradual does not mean uneventful. At the void's boundary, the physics of galaxy formation and evolution shifts dramatically over relatively short cosmic distances. Inside the void, galaxies are isolated, old, and slowly dying. Just outside the void's boundary, galaxies sit in the early stages of filament environment. Gas flows along the filaments toward the galaxies. New stars form. The environment feeds the galaxies in ways the void's interior cannot. The boundary zone is where the transition happens. Galaxies near the void's edge sit at a crossroads between two environments. Their gas reservoirs are being fed by the modest gas flows available near the void's boundary, less than galaxies deep in a filament receive, but more than galaxies in the void's interior have access to. Their star formation rates are intermediate. Their ages and chemical compositions bridge the gap between the old, quiet void galaxies and the younger, more active filament galaxies. This gradient makes the void boundary scientifically valuable. By studying how galaxy properties change as a function of distance from the void center, astronomers can directly measure how cosmic environment shapes galaxy evolution. The Boötes void, with its enormous size, provides an especially clean version of this gradient. The interior to boundary transition spans hundreds of millions of light years, large enough to study in detail with modern surveys. There is also a dark matter signal at the void boundary. As matter drained from the void's interior over billions of years, it accumulated slightly at the boundary zone before flowing further outward toward the denser filaments. The result is a subtle enhancement in both galaxy density and dark matter density at the void's edge, a thin, overdense shell relative to both the empty interior and the surrounding cosmic average. Cosmologists call this feature the void shell. It appears in simulations of structure formation as a generic prediction. Voids should be surrounded by a slight overdensity at their boundaries. Finding and measuring this shell around the Boötes void would confirm that the void formed through standard gravitational drainage, rather than some more exotic mechanism. The shell is also a target for gravitational lensing measurements. Light passing through the overdense shell at the void's boundary gets bent slightly by the extra mass there. By measuring how light from distant background galaxies is distorted as it passes through the shell, astronomers can map the dark matter distribution at the boundary with precision that direct galaxy counts cannot achieve. Those measurements are being attempted with current instruments. The precision is not yet sufficient to produce a detailed map of the Boötes void's dark matter shell. But the target is clear and the tools are improving. When the map arrives, it will connect the void's interior history to the structure of the surrounding cosmic web in a way that no single observation has yet achieved. The boundary is where two universes, the nearly empty and the richly structured, press against each other across cosmic time. And in that pressure, the void leaves its most legible mark on the cosmos around it. The dominant view among cosmologists is straightforward. The Boötes void is extreme, it is unusual, it is rare, and it is still explainable within the standard model of cosmic evolution without invoking any new physics. The argument runs like this. Run the lambda CDM model through a computer simulation a large number of times. Generate simulated universes. Count how many of them produce a void as large and as empty as Boötes in a volume of space equivalent to the observable universe. The answer is, some of them do. The probability is low, but not zero. The Boötes void, on this view, is the tail of a statistical distribution, rare enough to stand out, common enough across all possible universe histories to require no special explanation. That argument is scientifically sound. Statistics allows for rare events. Finding one unusual structure is not evidence of a broken model. It is evidence that the model's full range of outputs has been sampled. The standard model predicts that extreme structures exist rarely. We found one. The model is confirmed, not challenged. And yet the answer feels incomplete to a growing number of researchers. The discomfort is not with the statistics of one void. It is with the accumulation, the Boötes void, the cold spot supervoid, the Hercules Corona Borealis Great Wall, the giant arc, the KBC void surrounding our own galaxy, the persistent Hubble tension, each one individually explainable as a rare fluctuation or a measurement nuance. Together, they form a list of structures and tensions that each require invoking the unlikely end of the statistical distribution. Science has a name for this kind of discomfort. It is called fine-tuning. A model that regularly requires its most improbable outputs to match reality is a model that may be missing something. Each invocation of luck is not proof of failure, but every additional invocation makes the pattern harder to dismiss. The honest position, the one that most careful cosmologists hold, is that the standard model is almost certainly correct in its broad outlines and may be incomplete in details that matter. The universe it describes matches observations remarkably well. The anomalies are real, but manageable within the model's current form. Nothing yet seen definitively breaks it. Definitively is the weight-bearing word. Science does not progress by waiting for definitive breaks. It progresses by following tensions until they resolve. The Boötes void is one tension. The Hubble tension is another. The large-scale structure anomalies are a third. Whether these tensions resolve by confirming the standard model at higher precision or by revealing a modification that improves it, they are worth following seriously. The Boötes void has spent 45 years being unusual. It spent the first 20 of those years being explained away as a measurement artifact. It spent the next 20 being incorporated, awkwardly, into the standard framework. It is now in a third phase, where new surveys and new measurements are returning enough precision to test whether the standard explanations fully hold. The answer, when it comes, will be one of two things. Either the void fits the model more comfortably than the rough early data suggested, or it fits less comfortably, and the model will need a new version that can accommodate it without relying on luck. Either result is progress, and either result will change how we understand the largest empty space we have ever found. Every structure in the universe has a fate. Stars burn out, galaxies collide and merge. Galaxy clusters grow denser as matter falls into them from surrounding filaments, and voids keep emptying, growing, and deepening across timescales that no civilization will survive to witness. The Boötes void is not just a record of the past, it is a preview of the future. The universe currently sits in a middle age of sorts. Structure formation is still active. Matter still flows along filaments. New stars still form. Galaxy clusters still grow. Voids still deepen. The cosmic web is a living system, not a frozen one. But it is aging. The rate at which new structure forms has been declining for billions of years. The universe's star formation rate peaked roughly 10 billion years ago and has been dropping steadily since. The energy output of the cosmos is gradually dimming. Dark energy is the reason the future grows dark. As the universe's expansion accelerates, the distances between gravitationally unbound objects grow faster and faster. At some point in the distant future, regions of the universe that are not already gravitationally bound to each other will pass beyond each other's cosmic horizon. They will become permanently invisible to each other, separated by distances that light can never cross. When that happens, the cosmic web will stop being a connected structure. Each bound system, each galaxy, each cluster, each group will become an island. The filaments connecting them will have stretched beyond functionality. Matter will no longer flow from one region to another. Structure formation will end. The Boötes void is already several steps ahead of the rest of the universe on this journey. It is already an island. Its interior galaxies are already separated from the surrounding cosmic web by hundreds of millions of light-years of near-empty space. The processes that would fill it, matter flowing inward along filaments, gas cooling, and forming new galaxies, have already stopped being relevant to its interior. The void has reached its terminal state ahead of schedule, simply because it started with less matter and therefore had less gravity to resist the expansion. Astronomers sometimes describe voids as the future of everything. The cosmic web will, given enough time and dark energy, gradually look more and more like one enormous void. Bound structures, galaxies, and clusters will persist inside it, but the connections between them will fade, the filaments will empty, the walls will thin, and the universe will approach a state where the great nothing is not an anomaly but a description of the whole. The Boötes void gives us a look at that state from a safe distance, an enormous region of the universe that has already settled into isolation, already stopped forming new structure at any meaningful rate, already begun the long, quiet fade that the rest of the cosmos will follow over tens and hundreds of billions of years. 45 years ago, a team of astronomers found a blank patch on a galaxy map and named it the Great Nothing. They could not have known they were looking at the future. The void is not a mystery waiting to be explained away. It is a window. Through it, we see where everything is going. Empty, quiet, vast, and patient. The universe does not end with fire or collision. It ends with space between things, growing until the things can no longer find each other. The Great Nothing was never really nothing. It was a clock, and it has been running since the beginning.